Hello, everybody. I'm very happy to be here today to introduce Chris Jeuell to you. I know Chris because we worked together on the AIME committee about 10 years ago, and Chris, I knew him by name before I actually met him because Chris has been a long-time problem writer and editor and contributor to the AIME and the AIMC contests and the MISMO and the ARML, all those contests that you're familiar with and that you love. And so I'm very confident that what he has to tell us today is going to be most interesting. I know I'm looking forward to it. And I invite you all to enjoy it as well. Thank you.
Okay. Thank you very much for that very generous and gracious introduction, David. So, yes, my name is Chris Jeuell. I'm actually not from around here. I'm from Washington, the Seattle area, so it's great to be back in New York. This is my first time visiting the New York Math Circle, so really thrilled to be here. And my talk is on what I call problem solving versus answer finding. So we will get into kind of what that's all about and the format of the talk in a minute. But for those of you who don't know me, and I guess I don't know almost all of you, when I do these talks, my style tends to be interactive. So for that reason, I'm going to ask lots of questions, and I'm going to encourage audience participation. Likewise, if you have a question yourself, if something's not clear, or if you have an idea to suggest, feel free to put up your hand, and I'll call on you, and we'll try to get to as many different solutions to the same problem as possible. What else? And because I don't know most of you, it's probable that if I call on you, I may ask your name just so that I want this to be more of a dialogue than a lecture proper, so to speak. So just so I get a sense of the composition of the audience, how many of you are in grade school or elementary school? Show of hands. Okay. Okay. How many are in middle school? Okay, I'm thinking that's a majority. Okay, and how many in high school? Okay. How many are like in dental school? Or grad school? Okay. So, as I said, I tend to ask a lot of questions, and so just to kind of open this up, my first opening question is problem solving versus answer finding. So I'm kind of making a distinction or a contrast between the two. Who has an idea of kind of what makes these two activities different? Yeah, and your name? Your name?
Artem. And in problem solving, what you do, you tend to try to solve the problems using like different equations, things like that. But in answer finding, you usually more like guess and check your answers and try to guess your way through.
Okay, so got some good ideas there. With answer finding, it's more of guess and check. With problem solving, it's maybe a little bit more involved, some equations and stuff. You have an idea? Oh, and your name is?
Martin.
Martin, okay.
I think answer finding is more of like what you do for your teacher.
Okay.
Your teacher asks you to find
Answer finding is what you do for your teacher, okay.
Whereas problem solving is sort of what you do when you want to find something out for yourself.
Ah, that's an interesting distinction. So finding the answer for your teacher versus yourself. So, okay. And just continuing on that point a little bit, when you're finding an answer for your teacher, obviously we want to do like correct answer finding. So it's all about the answer, right? It's all about did you get the number right or not, right? Whereas problem solving, I argue, and maybe this is going to continue to sort of make itself apparent, problem solving is a little bit deeper and a little less kind of directed. So you had an idea? Yes?
Problem solving is like, well, at first answer finding. Answer finding, I think of as more raw calculation.
Yes, absolutely. Very mechanical. And do you have any ideas about problem solving? Kind of what defines that? What makes that unique?
Problem solving is not so much about solving the equation, but actually finding the equation. Probably
Right.
more likely words that you're given.
Right. So I make the argument that problem solving, and by the way, I will sometimes interrupt myself as I think of these things, but how many of you have heard of art of problem solving? Show of hands. That's like almost everyone. And some of you, if you were asked to describe that to someone who didn't know what that was, you might say, well, that's an online forum, you know, and community and portal for discussing like math competition related stuff. But there's no math anywhere in its title. It's problem solving that is sort of the focal point, okay? So the point being that problem solving is a technique and something that is, in some cases, hard to teach directly. It can often be taught through example. And we're going to do one example, and you're going to see in very apparent manifestations different ways of sort of attacking the same problem. So problem solving is not just scoped to mathematics, and I would argue it's at a deeper level than just finding the answer and did you get the number right or not. So another question to kind of gauge the audience and sort of make sure I know who I'm speaking to. How many have done or will do math counts? Okay, so here's a great example. To me, the ultimate example of answer finding is the countdown round, right? Because the countdown round, every problem, you have at most 45 seconds, and then the problem's over. And you know, it's often a very simple like trick or something, and you, as you said, as you pointed out, it's often just a routine calculation or something very mechanical and not a lot of deep insight involved. So, I mean, I swear, when I watch these countdown rounds, you know, it's like they flash the problem, and before you can even blink your eyes, someone raises his hand, and it's like, square root of 17 over 5. And it's like, how did you get that? So, that's a little crazy. So, anyway, problem solving, yeah, is a deeper activity. So, with that out of the way, I'm going to put up a problem, and we're going to pretty much spend the hour talking about different solutions to this problem. Excuse me here. So the problem is find the distance So find the distance from the point 2, 3 to the line y equals x minus 1. Okay? And by the way, I see a lot of you taking notes, which is a good thing. So I encourage people to take notes. Even if you can watch the video later, I think taking notes and writing things down helps you really internalize kind of what I'm communicating. Even if it's just something that you say, oh, I know what this is all about. I know how to solve this problem. Because as I said, we're not just going to solve this in the pedestrian way. I'm going to solve this in at least 8 different ways. And you may be bored, and if that's the case, then I guess come back next week and you'll hear a different lecture. But I would argue that some of these ways are very subtle, they're very sophisticated, and I would say that, well, so how many of you are aware that there is a formula for this particular problem? Yeah, there's a formula. And I'm not going to ever mention it or write it down. Now, many of these methods that I'm describing can help you derive that formula, which is a useful thing. But I would argue that if all you know is the formula, and if all that you're able to do is apply that formula to this one problem, that's not as valuable, that doesn't make you as valuable a problem solver as if you understand like different ways of sort of looking at the same thing and kind of tackling a problem that has a bit of complexity and abstraction, okay? So I left some gaps here intentionally because I'm going to give some variables or some names to these things I'm talking about in the problem. So I'll call the distance that we're trying to find d, and I'll call this point 2, 3 point P, and I'll call this line L. Okay? And so before I even go into the solution, I guess I'll throw out what I would call maybe step 0 of reading and sort of solving a problem, which is making sure that in your own mind you are clear on what is it that you're being asked to do. So you might think mentally of a diagram, you know, like you have a line here and then you have a point. Let me draw a better point. So like if you were sort of uninitiated or haven't seen a problem like this, you might say, well, what does it mean, the distance? I mean, there's lots of distances from this point to this line, right? I mean, you know, like, what does it mean, find the distance? Like, lots of ways to draw a line from the point to the line. So, yes, and your name?
My name is Ben. From the point to the line where in which is perpendicular.
Okay, yes. So when you see the phrase the distance, what is implied is really the minimal distance. Let me redraw this picture. So we have a line L, and we have a point P, and so we really want the perpendicular distance, which happens to be the shortest distance to the line. So, you know, before we sort of launch into a solution or doing sort of maybe the obvious thing, just mentally clarifying, do I understand every word, every sentence? Have I read all of the given information so that I can really, you know, go about starting to solve this thing? And just as an aside, I mean, this intuitively kind of makes sense, this notion of shortest distance. Like, let's say P is a person, right? And L is the other side of a street, and a person is trying to cross the street. You know, most of us, when we cross the street, we cross at a right angle to the street, because it's the shortest distance, and therefore minimizes the time that we're in the street. And, you know, or we don't want to get too much exercise, or we don't want to expose ourselves to hazards in the street, such as some of the drivers in this town. So anyway, so we know clearly now we want perpendicular distance. So for my solution, and I'll number these solutions, and then after each solution, I'll sort of give a very short, like 2 to 5 word summary of the essential ideas. This one I'm just going to call the classical approach, which is my guess as to how most people would attack this problem. So we have a point, we have a line. Any idea for sort of a reasonable first step to get started on this? Yes?
I have a question. What
Question.
do you mean by y equals x minus y?
Ah.
I kind of don't understand what they mean by that.
Right, so this is a coordinate geometry problem, and in the coordinate plane, so you have the x-axis, you have the y-axis, and they intersect perpendicularly, so something like this. So your x-axis is the horizontal, the y-axis is vertical. And if we put tick marks to label unit steps along each of these lines and treat them as number lines, we can, for example, plot points using this scheme. So for example, the intersection of these coordinate axes is known as the origin, and that's the point 0, 0. So for example, if I told you a value of x, like x equals 2, then plugging that in, what would y be equal to?
Y would be equal to 1.
Y would be equal to 1. So we count off, we go 2 steps to the right, because the right is the positive direction. So if x equals 2, then y equals 1. Can we find some other points on this line? Like, what if x equals 1? Then y equals 0. Okay.
So it's like basically a slope in that too.
Yeah. So turns out if we start plugging in values of x, this is kind of giving us a formula for how to calculate the corresponding y value, or the vertical offset. And so you're actually getting to a suggestion that I was going to try to draw out of people for the first step to do. So when you sort of plot all the different possible values of x when x ranges over the real numbers, you end up getting a sloping segment, as you pointed out, so a line. So essentially, now here's this point P, 2, 3. Where should I go to plot that? So I count over 2 steps to the right and then 3 steps up. So I get to point P is somewhere like this. Okay? and we want the minimal distance. So we want, because P does not actually lie on this line, so we want the shortest distance to go from P to the line, so perpendicular distance, okay? So, anyway, you have a coordinate geometry problem. You're given the equation of a line, you're given a point. What seems to be a logical first thing to do if you haven't sort of seen this problem format before? Yeah?
You could graph both the line and the point.
Absolutely. So I'm going to summarize that as draw a picture. And I'm not just going to draw a picture, I'm going to draw an accurate picture because in some cases that will be immensely helpful. So as the saying goes, a picture is worth 1,000 words. So we have our coordinate axes, y and x, and I'm going to mark off tick marks for unit steps. Like so. And it suffices to plot 2 points that lie on the line, and then we've got the line. So for example, when x is 0, the y-intercept of this line is -1. So I'll draw that as we have this point lying on the line. And then when x is 1, as was pointed out, y equals 0. So we have a line with a slope of 1. So it'll look something like this. That's my L. And then let's plot point P. So that's 2 over to the right and 3 up. Point P. And we know that we want perpendicular distance, so we drop a perpendicular and we try to draw it very accurately to this line. Now, if I were doing this on graph paper, I think it would be a little bit more evident, but actually maybe the tick marks should look something like this, because if we sort of look at the foot of this perpendicular where it intersects the line, what point, if they had to be integer coordinates, which they aren't necessarily, but anyone have a guess as to what this intersection point is from P to the line? Yeah? Huh? Is the what? The, huh? The x coordinate, yeah. So it turns out, so let's call this foot of this perpendicular, let's call this point Q. If you kind of eyeball it, it looks like, yeah, this is pretty close to the x coordinate 3. And because it lies on the line, if the x coordinate is 3, then what would the y coordinate have to be? Yeah? 2. So, like I said, if I had graph paper and if I drew an accurate diagram, you could actually eyeball this, and without really even needing to solve anything, you'd say, that looks like 3, 2. I should point out that in general, this is not a very reliable strategy in that if I gave you an arbitrary line and an arbitrary point, most people are not able to eyeball it and say, yeah, that looks like 2/7 pi over 2. It doesn't work like that. So, but in this case, we can verify that this point is indeed on the line and that PQ is perpendicular. But if we, had a different line or a different point, for example, what we would really want is, like, can we find an equation for the line through point P that's perpendicular to line L? What would we need to have? We know it passes through point 2, 3 because that's what we're given. So I see some hands. So yeah.
Find the slope and the y-intercept.
Right. So we know that L has a slope of 1. And so if we consider segment PQ, knowing that PQ is, by construction, by the problem statements, perpendicular to L, what must be the slope of line PQ? Someone I haven't called on. Was there someone over here? No? All right. Oh, yes. -1, yeah. So it's a kind of well-known fact from algebra, coordinate geometry, that I take the negative reciprocal of the slope of the line that I'm perpendicular to. So line PQ has slope -1. And we know also that it passes through the point 2, 3. So for line PQ, some of you may have seen the point slope form of writing the equation of a line. I can write simply y minus 3 equals -1 times quantity x minus 2. Notice that the point 2, 3 lies on this line segment, and this line segment has slope -1. And so if we sort of multiply the right side out and then rearrange, we get what? Y equals what? Yeah.
Y equals -x plus 5.
Yeah, y equals -x plus 5. So now we have an equation for this line that goes perpendicular to L and passes through this point 2, 3. And the line L is given to us as having equation y equals x minus 1. And so now we have a system of two simultaneous equations, which I won't belabor the algebra, but we can solve. And sure enough, we can confirm that the solution of this system is x comma y equals 3, 2. Okay? So we're almost there, but is that the answer, 3, 2?
No.
No, because we're asked to find the distance. So how do we finish this off? And I'll erase this diagram here. So now we have, we figured out the coordinates of point Q. That's good. So what now? Yeah.
We must find how much it takes from 2, 3 to 3, 2.
Yes, we must find the distance between points 2, 3 and 3, 2. So how do we do that? Yeah.
Well, the 2, 3, point 2, 3 and point 3, 2 are on opposite ends. If you're on graph paper, they're on opposite ends of the square. So if you draw that line on the square, it's an isosceles right triangle, and the side lengths are 1, 1, root 2.
Yes, yes. So that's one way you can think about it. You can also think of if I draw a line through P that's perpendicular to the x-axis, which I didn't draw very well because it should have intersected 2. And if I draw a dotted line through Q, essentially I'll have a right triangle. And if I sort of look at this vertical distance, if I'm just concerned with the vertical distance from P to the horizontal through point Q, basically what's the change in the y-coordinate from P to Q? I'm going from 3 to 2, so that vertical distance is therefore equal to what? It's 3 minus 2, so it's 1. And similarly, the horizontal distance, when I go from P to Q, is from 2 to 3, so that's also 1. So yes, I have an isosceles right triangle, and therefore the hypotenuse is square root of 2. How many know the Pythagorean theorem? Okay, it's almost everyone, that's good. So you might have also seen in coordinate geometry the distance formula, which in general says you square the difference of the x-coordinates, and then you add that to the square of the difference of the y-coordinates. And essentially, it's this drawing lines that are perpendicular parallel to the coordinate axes, and then you have just linear distance, so you take the difference of the x-coordinates and y-coordinates and square them and so forth. So we have found that, and I'll write it as, if I do the difference of the x-coordinates of P versus Q, that's 2 minus 3 squared, plus the difference of the y-coordinates of P and Q, so that's 3 minus 2 squared. And so square root of 2 is our answer, right? So some people who are in the answer finding kind of frame of mind, they might see this and say, okay, we've kind of figured out everything there is to figure out, right? We know this point Q, which is the point that, the foot of the perpendicular from P to line L. We figured out an equation for line PQ. We've calculated the distance using the distance formula. What more could there possibly be? So that's how maybe an answer finder would think about this. But we're going to sort of explore some different approaches for getting to the same final answer that are maybe not so obvious. So here's solution 2. And generally with these solutions, as I said, I'm going to number them, and I'm going to give a short summary of maybe the key idea, and I'm going to kind of start them off, and then I'm going to ask you to kind of help me finish them off. And we're not always going to calculate the distance. You know, for example, we might stop when we get to 3, 2. Or we might stop if we end up solving for the distance and not even need to get this point 3, 2. Is there a question?
I have a question.
Yeah.
When you do the d equals root, that equation right there.
Yeah.
Sorry, which one would be like the x coordinate and y coordinate?
So, I mean, I intended for this to be, if I can label it like this, let's say the x coordinate from point P minus the x coordinate from point Q plus the y coordinate from point P minus the y coordinate from point Q. You can take the difference in either order because you're squaring them, and you can add these squares of differences in either order because, you know, addition is commutative. You can't do xp minus yq, though. That's just silly. Yeah. Okay. So solution 2. And I'm going to call this the solution with a moving point with a pivot on the slope. And again, I'm going to draw my diagram. So here's line L, and two comma 3 is here, and we want to find this minimal distance D. So the way I'm going to set this up, and it's actually a very similar solution to solution 1, but let's just say that I have I take some random point on the line L and I call it P prime. And suppose that the coordinates of P prime, suppose I tell you that the x coordinate of P prime is T. Then what, if this point P prime lies on the line, must be the y coordinate? Yes?
T minus 1.
T minus 1. Because that's what it means for a point to lie on the line, right? So essentially what I'm doing is I am parameterizing an arbitrary point that lies on the line by saying, well, if I'm given that the x coordinate is t, then in order to be on the line, the y coordinate has to be t minus 1. And I think you'll agree, I hope you'll agree, that if I gave you a value of t that corresponded to the x coordinate, then you could generate a point lying on the line by just saying t minus 1, and then you plot that. So every real value of t gives you a point on the line. And conversely, for every point on the line, I can find a value of t that will, satisfy this form, t minus 1, because that's what it means for a point to lie on a line. So we have this kind of nice one-to-one correspondence. So I've kind of fixed this point to already lie on line L. And going with the idea that we want this segment PP prime to be perpendicular to line L, I claim that we can write an equation based on this general form of a point that lies on the line L so that we have that this line has the correct slope. So as was pointed out in the first solution, we want the slope of PP prime to equal what? -1, the negative reciprocal of the slope of line L. So can we generate an equation for segment, or not an equation, an expression for the slope of PP prime in terms of this parameter t? What would that look like? I have 2 points. I want to find the slope between those 2 points. What's the rise over run? What's the definition of slope? Yes?
y1 minus y2 over x1 over x1.
Right. So applied to this particular example where I have the point 2 comma 3 and then this point t minus 1, tell me what to write down for the slope. What's the difference of the y coordinates? Yeah?
3 minus t plus 1.
Huh?
Well, it would be 3 minus parentheses t minus 1.
Yeah, so I could do 3 minus t minus 1. Okay, and the difference of the x coordinates, taken in the same order, is
2 minus
2 minus t equals -1. So if I multiply through and if I simplify this a little bit, I get that 2 minus t equals t minus 2. And that implies that what? T equals anyone? Yes? 3. So I claim that now we've pretty much solved the problem, right? Because now we've found the value of t that causes segment P prime to be perpendicular to L. And so given the t, which is my x-coordinate of P prime, I can generate the y-coordinate, which is 2. And that gets me back to this point where I figured out this point Q, as I labeled it, 3, 2. So we've figured out we've sort of created a condition on t such that the resulting point that we get will end up being the segment will be perpendicular. So I think I saw a hand up for a question. No? Okay. So it's essentially the same mechanics. Essentially what I did is by parameterizing this point P prime, I forced this point Q that we were sort of looking for to already lie on the line that we are given. So instead of solving a system of equations, I've just set up an equation involving slope and have figured out the value of t that gives me my magic point Q. And then again, is this the answer? No, it's not the answer. The answer is we have to now use this, plug this in, and calculate based on the distance formula, but it's the same calculation, right? So here's another solution based on the same idea, but actually has a very different flavor. So this is, again, a moving point, now with a focus on distance. So again, and as the time goes on, my diagrams may be less accurate, but will hopefully generally convey the idea. So here's my point 2, 3. Here's my line L. And again, let's say that I have an arbitrary point P prime lying on this line with coordinates t, t minus 1. Well, before we set up a criterion for t so that the resulting segment was perpendicular. But we also discussed at the beginning that perpendicular distance is the same as minimal distance. So one idea is let's calculate this distance of this segment from the point 2, 3 to the point t, t minus 1 as an expression in terms of t. So again, using the idea of the distance formula, which really is same idea as the Pythagorean theorem. I draw some imaginary lines and I do the difference of x coordinates and y coordinates. So what's one thing that I should write under this square root expression to calculate the distance? Yeah?
T minus 2 squared.
Right, so I take the difference of the x coordinates and I square it, so that's t minus 2 squared. And then now what's left?
Then it's t minus 1 minus 3 squared.
Yes, exactly. Difference of the y coordinates. So, simplifying that a little bit, t minus 2 squared plus, this will be t minus 4 squared. And what do I get when I expand t minus 2 squared? Yeah? T squared minus
4.
t squared minus 4? Does everyone agree with that? I think you're squaring each of these and then subtracting, but squaring is not distributed. Yeah. You and I? Right. Using the results of multiplying binomials or squaring binomials. So yes, I get t squared minus 4, t minus 4, or sorry, plus 4. And then what do I get when I square t minus 4? Yeah.
T squared minus 8t plus 16.
T squared minus 8t plus 16. So when I simplify all that stuff under the square root expression, what do I have? When I simplify and clean it up, what does that simplify to? Yeah.
2t squared minus 12 plus 20.
2t squared minus 12t plus 20. Okay. So what have I done? I have calculated in terms of t the general distance between some point with x coordinate t to this other point with coordinates 2, 3. So in terms of t, that's the square root of this. What kind of function of t is this under the square root sign? Quadratic, yes. So as we sort of talked about before, we want to make this, we want to minimize this. We want to make this as small as possible. So does everyone agree that if we wanted to make this as small as possible, that would be the same as we want to make the thing under the square root be as small as possible, because the square root function is increasing, right? So if we just consider what's under the square root sign, 2t squared minus 12t plus 20, it's a quadratic. And in general, when I have the graph of a quadratic, what is the graph called? Parabola. And so in this case, if I were to graph this with t as the independent variable, so it's on the x-axis, I could either have a picture like this or a picture like this. So which would my picture look like if I graphed this function? The one on the left or the one on the right? The one on the right. Why? Because what? Because this coefficient of the t squared term is positive. So we know that this won't be the picture of our, if we graph this as a quadratic in t, it'll be this picture. And so we essentially want to find the y-coordinate of the vertex of this parabola. And this picture also supports the idea that this function achieves a minimum value. So anyone know how we find the minimum or the vertex of a parabola? Anyone help me once we have this expression here? Oh, yes?
X equals minus 0 to x.
Right, so I'm hearing, and I'll try to avoid things like x and b and a because here we just have constants in t, but in general, to get the, I'll call it t min, the minimum value, or the t that generates the minimum value, we take the negative of the coefficient of the t term, so that's negative of negative 12, and then divide by 2 times the coefficient, the leading coefficient, which in this case is 2. And so when we do this calculation, we get t min, the value of t that generates the minimum value of this function. What does this simplify out to? 3. Oh. So we're back here. Got the same value of t. If you didn't happen to know the formula for finding the vertex of a parabola, we could have also factored out a 2 and written this as t squared minus 6t plus 10. And what if we were to complete the square on this quadratic, just knowing the first 2 terms? What constant would we have to add to get this to be a perfect square trinomial? 9, right. And then because I was really adding 10 as part of this function, well, 20, but then I factored out 2. So then what would I have to add to make this come out to 2t squared minus 12t plus 20? I'd add 1, okay? So, just gonna erase this stuff around here. So I'll call this actually d min because really, and d min is really the square root of this thing. So I have that this is the square root of 2 times t minus 3 quantity squared plus 1. And as we mentioned in this second solution, t ranges over all the real numbers. So knowing that I'm squaring a real number, what's the smallest possible value of the square of a real number?
Is it a 1 or a 2?
Oh, good point, thank you. Right, I have to distribute the 2. So how would I minimize just this thing? I'm squaring a real number. So what's the minimum value if it's a real number? If t is a real number? Yeah? Well, t would give me the minimum, so t would cause this expression that I'm squaring to be 0. So basically, every perfect square of a real number is greater than or equal to 0. So once again, if we write it sort of by completing the square, we not only get the value of t that corresponds to this point q, but we've minimized this quadratic because this becomes 0, and we have that the minimum distance is the square root of 2, which is, as we discussed before, the number that we are looking for. By the way, problem solving, I mean, if you know 2 different ways to solve a problem, that can be very helpful in the following sense. That if you have a problem, let's say on a contest, you solve it one way, you get one number. You solve it another way, you get a different number. I hate to burst your bubble, but if that happens, then at least one of your answers is incorrect. It could be that both answers are incorrect. Whereas if you solve a problem 2 different ways and you get the same number, that doesn't guarantee that you have a correct answer, but it does increase the probability that you are probably doing the right thing. So I would say that if we solve this problem 9 different ways and we end up getting the same number, it's probably likely that we've gotten the same number. Now, an exception to that is if perhaps we make a bad assumption somewhere along the line, and if we carry that assumption through to all of our solutions, then you're sort of out of luck. But if you solve the same problem in 2 different ways and you don't end up with matching answers, that means, you know, you need to check over your work. And, you know, sometimes it's a faulty assumption, sometimes it's just a simple arithmetic or algebra mistake, something like that. So, all right, now on to solution 4. And I'm going to start speeding up here. And in favor of getting to as many solutions as we can, so you can just see the different number of ways of looking at this. So solution 4 is based on similar triangles. So here's this point P with coordinates 2, 3, and let's drop the perpendicular and let the foot of the perpendicular be point Q. And because we have a right angle here, and because our coordinate axes intersect at right angles, one thing that can be helpful is to draw in extra lines. And so the line that I'm going to draw in this particular solution setup is I'm just going to drop a perpendicular from P to the x-axis. Okay? And I'll let the foot of this perpendicular be point C. And then I'll also label the intersection of line segment PC with line L, I'll label that as point B. And then finally, I'll let the x-intercept of line L be point A. So I claim that there is a pair of similar triangles. What are they? What's one of them? Yes, back there.
I can't quite see the points, but PQ and that there's 3 and all.
So P, Q is the foot of the perpendicular, B, A, and C. Does that help?
Okay, so PQB.
Okay, so triangle PQB. And let me maybe color in this triangle so we know what triangle we're talking about. So you go PQB is similar to what? What's the, what should the correspondence be? So yes?
A, B, and C.
A, B, C, does that work? Is that the right, let's see. Is this the right correspondence of vertices? PQB. Well, let's why are we saying these triangles are similar? Well, they're right triangles, but then they also share a vertical angle here. So we have two pairs of congruent angles. So I agree that PQB, that's one triangle. What would be the corresponding similar triangle if we needed to get the vertices in the right order? I agree we can start at point A, but to sort of know that we got the right correspondence, I think I heard it. What ACB, yeah. And a good check on this is Q in this diagram was the vertex of the right angle, right? And if we sort of flip over this triangle so that P sort of lines up with A, then we know that we should start, P and A should be in correspondence. And then Q, the right angle vertex, should be in correspondence with C, the angle of the right angle of triangle ABC. So we have this similarity relationship. And now what I'm going to do is, well, in red, I'm going to label the distance D that is sort of the unknown in this problem. And then I'm going to label distances that we can either immediately read off or find out. So for example, what are the coordinates of point C? Yeah?
It's 2, 1.
2, 1? C lies on the x-axis.
Yeah, so it goes 2x and then 1y.
But see, if P lies on the x-axis, then doesn't the y-coordinate have to be 0?
Oh yeah, yes.
So I think you're answering a different question, which is this point B, it lies on the line L. So because I've drawn a vertical through this point P whose x-coordinate is 2, the x-coordinates of B will be 2. What would the y-coordinate have to be? It lies on the line y equals x minus 1. So therefore, what's the y-coordinate? That's, yeah, right. So if I label, okay, and then A has its y-coordinate is 0 and it lies on this line, so what must be the x-coordinate of A? Yes? 1. Okay. So here I have labeled all of the points except for Q, and Q, of course, that's what I would like to know. But having sort of labeled this, now let me see if I can mark off some distances. So what would be the distance AC? It's the distance from 1, 0 to 2, 0. So that is 1. Okay. And then what about BC? That's the distance between 2, 1 and 2, 0. So that is 1. And then PB, that's the distance from 2, 3 to 2, 1. So that is 2. Okay. And because you knew Pythagorean theorem, which is good, AB, therefore, because in right triangle ABC I have the legs, so AB would then be equal to what? Square root 2. Good. And we want to find D. And D is equal to PQ. So when we have similar triangles, we want to use that similarity relationship to set up a proportion in terms of the distance that we want to find and known distances. So whatever proportion we set up, it had better have PQ in it. And if it has PQ, what else does it have to have? It has to have what? It has to have AC. So what if I write PQ over AC is equal to what? We want more known distances. What else can we write? Yeah, in the back.
PB over
Yeah, we could do PB, which we know, over, and then the corresponding one would be AB. And then from this point, substituting in either the unknown, which is PQ, which is D, and then known values, so we know that AC is 1, we know that PB is 2, and we know that AB is square root of 2. We get that D over 1 is 2 over square root of 2, and sure enough, d is square root of 2. Notice that we didn't actually, in this solution, figure out what q was. We just used similar triangles and we got a proportion that gave us the desired distance. Okay? For this one, how many, by show of hands, know trig? I might skip this one if, okay, or at least right triangle trig. Okay, I think that's enough for me to kind of set this up. Before I launch into the solution, though, I want to do a little, as I am sometimes known to do, I want to do a little diversion, which is, because here's a question I expect fewer hands to go up for. How many people have had pre-calculus? Not the adults. Okay, how many students have had pre-calculus? Right, so I'm going to take a 2-minute diversion to derive a useful fact that comes out of pre-calculus that you probably don't even need to be in pre-calculus to learn, but it's a useful diversion in this particular problem. Okay, so let's suppose that I have a non-vertical, non-horizontal line, and its general form is y equals mx plus b, right? Where m is not equal to 0. So m is the slope and b is the y-intercept. So we all know this familiar fact. So if it's non-vertical, and if it's non-horizontal, then this line will make an angle with the x-axis, starting from sort of the positive x-axis, and then sort of moving counterclockwise until we sort of get to this line. So this angle theta is known as the angle of inclination. And so the point of this diversion is to come up with a relationship between theta and the sort of parameters that define this line, y, m, and b. And so the first thing I'll point out is that I can slide this line over so that it passes through the origin. And if I just do a parallel shift, well, what would the equation of this line be? It's parallel to this line y equals mx plus b, so the new line, the translated line, which I should probably draw in a different color and maybe put it in red dashes. So what would be the equation of this line where it's parallel but it's shifted so that it passes through the origin? Yes? Y equals mx, which makes sense. It passes through the origin, so my b should be 0, and it's parallel, so it should have the same slope. So I'm going to just duplicate this diagram over here just to make things a little bit cleaner. So I have y equals mx. And let's suppose that I have some arbitrary point on the x-axis. I'll call it x sub 0. What would be the corresponding point that lies on this line? I'll call this line L. So what would be the point with coordinates x sub 0? If x sub 0 is the x-coordinate of a point that lies on the line, what has to be the y-coordinate? Yeah? mx sub 0. And that makes sense because if you think of calculating the slope between the point x0, mx0, and 0, 0, you take the difference of the y's, the difference of the x's, and you divide them, and you get m. So that's all well and good. So this is the vertical distance, mx sub 0. This is the horizontal distance, x sub 0. But now I gave you this angle theta, which was the angle that this line made with the x-axis. So can we come up with a relationship between theta and that doesn't involve this x sub 0? Like, in terms of our trig functions, we have sine, cosine, tangent. So anything come to mind? Well, let me just ask the question, what is tangent of theta? Yeah?
I think that's sine of theta over cos of theta.
It is. By definition, it is sine of theta over cosine of theta. in a right triangle, that ends up being, I can end up taking a ratio of 2 of the sides of the triangle. So anyone know which, oh yeah, back there. Yeah, so when it's tangent of an angle, I take the side opposite that angle. In this case, that side has length mx sub 0. And I divide by the length of the side that's adjacent to the angle. And in that case, that is x sub 0. And so the x sub 0's nicely cancel, and I get that the tangent of this angle of inclination is equal to the slope of the line. So what I just derived, in which you often learn in a pre-calculus class, is if I have the line y equals mx plus b, and it makes an angle of theta with the x-axis, then the tangent of that angle will coincide with the slope of that line, okay? So I sort of went into this diversion because it'll be a particularly useful fact for this trig solution I'm about to set up. And by the way, I called it a diversion because I didn't want to make a bad pun by calling it a tangent. Okay, anyway, it is a tangent. So let's draw our diagram again. So this point P, 2, 3. And again, we have a perpendicular distance that we are trying to figure out. So for this solution, suppose that I draw the line through P that's parallel to the x-axis. And let me call this angle of this triangle, which I should probably label these points. So I'm drawing the line through P parallel to the x-axis, so parallel marks here. And where does this parallel line intersect the line L? Well, the y-coordinate of this parallel line is what? 3, right? And if there's a point that lies on L and its y-coordinate is 3, then what must be the x-coordinate of this point? I'll call this point P prime. So if I have 3 as the y-coordinate, what does the x-coordinate have to be? Yeah. Oh, or how about you? X-coordinate has to be 4. Okay. So here I've labeled 3 points of a triangle, P, P prime, and Q. And now let me measure of angle P, P prime, Q equal alpha, like this, okay? Can we identify another angle in this diagram that also has measure alpha, given that we have parallel lines? Yes?
I don't know how to.
Yeah, I don't have.
It's just like this one. Like
This angle of inclination.
Yes. And
The-
also there's another one, because if you continue the slope,
Uh-huh.
there's one over there.
Oh, sure, sure. Yeah, if I continue drawing this line, that's a good point. I have by vertical angles, here's another alpha here. Oh, there's lots of them actually. So yeah. Okay, so we have alpha here. What else do we know? Well, so we identified this point P prime as having coordinates 4, 3. So what is the length P, P prime equal to? In other words, the distance between 2, 3 and 4, 3 is 2. Okay. So let's put all this together and see if we can use some right triangle trig to figure some stuff out. If I look at triangle P, P prime, Q, by definition, what is the sine of angle alpha? That's this angle. The sine is equal to opposite over hypotenuse, right? So in this case, what would be my sine expression? D over 2. Opposite over hypotenuse, okay? Okay, so that's one thing, but because of the facts that I just rattled off about a line making an angle with the x-axis, what can we conclude about this angle of inclination in relation to the slope of line L? We can write that tangent of alpha is equal to what? What's the slope of line L? We're given that line L is y equals x minus 1, right? Yeah? The slope of the line is 1, and therefore the tangent of this angle alpha is equal to 1. Now, if I know that the tangent of, of an angle is 1, what can I conclude about the angle if it's an acute angle? The angle is 45 degrees. Okay, so now if I plug in sine of 45 degrees, I know that that is equal to what? Square root of 2 over 2. And this is supposed to equal d over 2. So with that, once again, I have d equals square root of 2. By the way, before I move on, when I did this similar triangle solution, just to kind of give you something to leave with and play with on your own, because I don't want this just to be me demonstrating solutions. I just drew, you know, we just kind of joked about how there's lots of angles that are the same congruent angle, but here we have PQ and line L. I claim that there's lots of different lines that I could draw to get similar triangles, so don't just always draw a vertical line through P. I claim that, for example, if I draw a horizontal through P and a vertical through Q, I claim that these two triangles are similar. See if you can prove that. I also claim that if I just draw the horizontal through P, I claim that this triangle is similar to, drop my chalk, this triangle where the vertices are taken in some order. So it's not necessarily that there's always a right sort of correct point to draw the line through. Sometimes you have to just kind of play around and try things until you get something that works. So here's another solution based on the Pythagorean theorem. Here, maybe at this point, since we're running short on time, I'm just going to kind of outline these. So for this solution, what I'm going to do is I'm going to choose any point on the line L except for Q. And for convenience, I'm just going to pick the y-intercept, and that's 0, negative 1. So I'm going to call that P1, 0, negative 1. Okay? And now I'm going to consider right triangle PQP1. Okay? And did I do this right? Oh, yeah, right. Okay. So I don't know the coordinates of Q, but I do know that because Q lies on the line, its coordinates are going to be of the form x, x minus 1, right? And so, well, the Pythagorean theorem tells us that PP prime squared equals PQ squared plus what squared? Square of the hypotenuse is the sum of the squares of the legs, so PQ squared plus what else squared? P1Q squared, right? So PP1, and by the way, I arbitrarily picked P1. I mean, the point is that it just has to lie on this line so that I have a nice right triangle. What is the distance between P and P1? Using distance formula, and actually I square it so I don't even need to worry about the square root. I take the difference of the x coordinates, square that, and I add that to the difference of the y coordinates. So that should be what? 2 minus 0 squared plus, what's the difference of the y coordinates? 4. So it's 3 minus negative 1 squared. And so when I simplify this out, this is equal to 20, right? Now, what's PQ squared? Well, that's 2 minus x squared plus the difference of the y coordinates. So that's 3 minus x minus 1 squared. Have we seen this before in an earlier solution? I think so. And then finally, what's the difference, what's the distance between Q and P1? This one's kind of easy, comparatively speaking. What's the difference of the x coordinates? I thought I heard it somewhere. X. So I have x squared, and then what's the difference of the y coordinates? I have x minus 1 minus negative 1. So what's that? That's also x. So what do I get when I expand this out and simplify? Well, because we're running short on time, I'm just going to put what we got from an earlier solution. That is x squared, no, 2x squared minus 12x plus 20. And then this is just x squared, right? So my 20s cancel, and I wind up with the quadratic 4x squared minus 12x equals 0. So what are the solutions to this quadratic? Four x squared minus 12x equals 0. Any solution? Oh, yes.
0 and 3.
0 and 3. So if I factor, I get x equals 0 or x equals 3. So 0 ends up being an extraneous root, but x equals 3, sure enough, gives us the desired point that we've been looking for. So we plug that in and we get 3, 2. Why does this root appear? Why does this extraneous root happen? What does this correspond to? Anyone have an idea? Maybe something to think about. If you study the diagram carefully and think about how it could arise, you'll understand why you don't want this, why this does not help you finding the distance. Oh, you have an idea?
That might be P prime.
Yeah, it ends up corresponding to this P prime here, which becomes like a degenerate right triangle. So very nice. Okay, I guess for the last 3 solutions, I'm going to just really set up the essential ideas and not necessarily run through all the mechanics. That way you can try them out on your own. So solution, what are we up to? 7? So and I'm going to call this the growing circle tangent to L. So here's the essential idea. Here's our point P, here's our line L. Let's say I have a circle who's centered at point P. And it has some radius, R. Well, I could first ask, how many intersection points does this circle have with this line, the circle that I've drawn up here? 0. It does not intersect the line at all. But as I grow this circle, it gets closer and closer to the line until at some point, when R is a certain size, this circle will become tangent to the line at point Q. And if we draw the radius from the center to the point of tangency, from geometry, we know what relationship does segment PQ have with line L? It is perpendicular. Okay. So here's the idea. Using coordinate geometry, if the radius of this circle is R, what's an equation for a circle passing through, so circle through 2, 3, radius R. What's an equation for that circle that I can write down?
X minus 2 squared plus x y minus 3
Yes, very nice. So in general, I do x minus the x coordinate of the center, square that, y minus the y coordinate of the center, square that, and I get the square of the radius. That's the general equation for this circle. Now, if it's going to intersect this line L, we know that an equation for line L is y equals x minus 1. So we could plug in y equals x minus 1 into here, and if we simplify this out, we will get a quadratic expression in x, right? But here's what we want ultimately. We want to know, for what value of r does that quadratic equation have exactly one solution? Because that's going to correspond to the value of x that causes this circle to have exactly one intersection point. So when you think of a quadratic expression, what must be true if it has one distinct real solution? What do we know must be true? Yes? The discriminant is equal to 0. So I invite you to plug this in and manipulate this with r being sort of treated as a constant. So in your ax squared plus bx plus c, manipulate this quadratic and then figure out the conditions on r so that the quadratic has a unique solution. And by the way, when you do that, you will be figuring out r without necessarily figuring out the value of x, although you can figure out the value of x. So that's one solution that you can do. What if instead I got the circle to be even bigger so that it intersected the line in 2 points? So let's see what we can do with this. So solution, the chalk's going all over the place. It's getting away from me. So solution 8, and I'll write growing circle chord. So in this solution, let's say that I have a point P, and it's the circle, and essentially what I'm going to do is, as with the Pythagorean theorem solution, I'm going to pick a point that lies on the line, and I'm going to draw a circle with radius, and I'll call this point P prime. I'll draw a circle with radius P prime, and it's going to, by construction, intersect the line at 2 points. So I'll call this point, let's say, P2. So I didn't draw this very accurately, but if I have a circle, then the radii are the same. And if I drop a perpendicular from P to the line in question and call that length D, and I'll call that foot of the perpendicular Q, what can I say about Q in relation to this chord? I'll call this point P1 instead of P prime. So chord P1, P2, what is Q in this chord? It is the midpoint, because we have congruent right angles, we have a shared side, and we have a shared radius. So we have that P1Q is equal to P2Q. And so what I claim is, if I pick any point on the circle, and if I write an equation for the circle knowing the radius because I have picked my point, and then I intersect that circle with the line y equals x minus 1, I can calculate the coordinates of P2, and if I chose, for example, the y-intercept 0, -1, I'll just tell you that if you solve this, you will get that the other point that intersects the circle is 6, 5. And so what's the midpoint of 0, 1, 6, 5? You average the x and y coordinates, right? So we take 6 and 0, we get 3. We take 5 and -1, add those, and we get 4, divide by 2, and that's 2. And that's what we've been getting at all along, is this point here. So lots of different ways. I didn't even cover all of the ways, but anyway, with that, that kind of does it for my talk. So thank you very much.
Thanks very much, Chris.
Yeah.
I guess we see that the problem can be solved in 8 or 9 different ways. And that's kind of the fun of the problem, not just the answer. Thanks again. See you guys next week.